All right, so this is a really short section here, just an intro, and it's really an introduction, and it's actually just a motivation for where the inverse scattering transformation comes from, because we're not going to go into all the details. It just gives you an idea about how this might connect. So the first thing to understand about this inverse scattering transform is this. Okay, this is a bit annoying. So this, computer's jumping a bit here. I managed to work out how to. I'm aware of that. Here we go. It seems to be working now. Just sometimes it does that. All right, inverse scattering transform. So it's a mapping. So we've got the KdV, which is this evolution equation, right? It basically tells us what the time derivative as u is, so we can step it. And we write it with the 6. And that 6 is kind of an arbitrary, it's just how we've chosen to write it when we non-dimensionalize. You could easily make that 1. Pros and cons of having it 6. I don't know which one's the better one, to be honest. Okay, so we have u of x comma 0 is equal to f of x. And we basically want to try and, the inverse scattering transformation is going to give us u of x comma t by a long and complicated process. But that's essentially what we're doing when we solve it numerically, isn't it? We time step and we get this u. All right. So, we saw before this transformation that's super important, and this is the mirror transformation. Okay, so what this does is, we saw before that we go u is equal to minus b squared minus dxv. Okay, it's another nonlinear equation for v given u. Now if we could solve that, and then we stuck it in and substitute, and we end up getting the modified KdV. Okay, it leads to this modified KdV, which I gave you before. I don't think I derived it, but you could pretty easily derive it yourself just by stepping through all the process. Okay. You end up with this equation like that. That's Mirror's equation. And if you substitute it in, you end up with a factor term out the front here, another term here, okay, with a derivative on it. So it's not entirely, if you can solve this equation, it'll definitely, and through this transformation, it'll definitely solve the KdV, but there is this sort of extra bit on here. Okay, so that's all good. Let's clear this. So this transformation, this mirror transformation, is itself a well-studied equation. And it's called the Riccati equation. And there's a special way to solve this, and it goes as follows. The idea is quite simple. You let v equal dx w over w, and then substitute that in here. So we get u is equal to minus v squared. So w is another unknown, it's another equation, but this is that we've got to solve, minus the x derivative of v. For the moment this looks horrible because this is very nasty and it's not going to be easy to solve. This is leading us nowhere. But of course a miracle is going to happen here. So we differentiate the top. Plus, right, because it's minus, something divided by, and then it's the xw, the derivative of the bottom times the top. And of course there's the miracle. Because, amazingly, that cancels with that. And we're left with u equals that. And we can rearrange that and get dx squared of w plus uw equals 0. Okay, which is an equation with u as a parameter. U is not, it's an equation in w with u as a parameter. Okay, and people found this scattering transformation is tied up with this equation. There's one last step to us to sort of the motivation for where this all comes from, far from a description of it. So we've got this, the KdV is invariant under this transformation. And the transformation is x goes to x plus 6 lambda t, and u goes to u plus lambda. All right, so what basically it does is we introduce a new function u hat, which is equal to u of x plus 6 lambda t. And we're going to see, so we've got a solution of KdV, and we're going to create another solution by scaling it. We're scaling the x with time. So these scalings are super important. This invariant is super important, the idea of it. Because we create quite a different looking solution. It's lifted it up and it's added this weird bit on. All right, so then we substitute here. Well, we get the u hat dt, and this is going to be a bit different, isn't it? Because it's going to be 6 lambda times the x derivative of u plus the time derivative of u. And the x derivative of u hat is just going to be equal to the x derivative of u. Now, if we substitute that into the equation, the KdV, the colour here, this one, we substitute that into the equation, so we have dtu plus 6, you can see where the 6 is going to come here, isn't it? We substitute into that, which is equal to 0, right? We're going to get the time derivative of u, which is this equal to, we're going to do this with u hat. We're going to get 6 lambda, the x derivative of u hat, plus the time derivative of u hat, plus 6. Now u hat, remember this is u hat over here, so u hat is okay, so we've got 6 u hat, and we've got the x derivative of u, which is just the x derivative of u hat is just the x derivative of u, and likewise this is just the x derivative of u. Then, okay, so we've got, sorry, I should have been careful. This is the time derivative of u, not u hat. Okay, the time derivative of u hat is equal to, all right, there we go. I made a silly mistake here. All right, we've got everything now in terms of u. And the time derivative of u hat is equal to blah, 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 which is written here, 6u hat. So then finally we substitute for u hat. So u hat is 6u minus lambda. And there's where the 6 is going to come into it. So they're going to cancel. So then we cancel those two terms. Get my special cancelling colour out. So that part there, the lambda bit, and that cancels. And we're left with the time derivative of u plus 6u x derivative of u. Okay, and that should be cubed here. Dx cubed u. Okay, so therefore, that if the u without the hat satisfies the KdV, then so will this. If this is equal to 0, then this thing here must be equal to 0 as well. Okay, so we've shown that transformation It's invariant under that transformation. Okay, great. So the only thing left is just to draw this conclusion here that leads us not to study the equation, because we've already got, we're going to get u goes to u plus lambda. So what happens if we do that? Then we take that equation we had, dx squared w plus uw equals 0, and it becomes like a u hat here, plus u hat w equals minus lambda w. And that equation is super important, and it is the Schrödinger equation. And it represents a lot of stuff in physics, which we'll talk about, scattering. And it's a very well studied equation. You will have studied this if you've done any physics at all. You know, scattering, well, electrons, tunneling, all of that stuff comes down to solving this equation. And this equation is going to be key in our nonlinear, in our inverse scattering transform.